So I'm Nathan Jackson. So yeah, I'm a professor at UNM in mechanical engineering department. Like I said, I work on MEMS or microsystems. So I'll use the two words like interchangeably. Microsystems is usually used in Europe. MEMS is usually used in America. And actually, if you go to Asia, it's usually micro machines. So but all three mean this exact same thing. So I use them interchangeably. But yeah, so my background's actually not mechanical engineering though. It's actually biomedical engineering. And then I did postdoc work over in Ireland, working in a national lab over there, more of microelectronics. So I've worked in almost every type of engineering discipline except for nuclear. I've done civil engineering, mechanical, electrical, chemical, material. So I've done it all except for nuclear. So who knows what the future holds? Maybe I'll go into that, but yeah. But you'll see why in a second, because in MEMS and microsystems, you need all those different disciplines. So and that's why I like it, and I'll get into that in a little bit. Let me see, change the slide. Okay. So Dr. Pyle did a good job of showing you like the clean room, showing you where we go to make these devices. But what I'm going to talk about is what type of applications do we work on, and mostly what type of applications we work on at UNM. Now, I could spend a whole day talking about all the different applications that we work on, but I'm going to focus on these two. So I'm going to focus on energy harvesting and also some biomedical applications, and just give you sort of a high-level overview of some of the different areas that I've worked on in the past few years. So briefly, so MEMS, so I know Dr. Pyle mentioned a little bit like where these are. So most people are not familiar with MEMS. I wasn't. Even as an undergrad, I didn't know what a MEMS. I didn't hear about MEMS until I was a graduate student. So you guys are already ahead of where I am. But yeah, so like MEMS, they're used everywhere, and everyone has some, and most people just don't even know it. Your phone, I'll hold it back to my screen so you can see it. Your phone. The current phones have about 50 to 200 different MEMS devices. So if you ever open up, this is not inside of a phone, but if you ever look inside like a computer or any electronics, and you see these sort of black little boxes in here, those are most likely, they could be processors and transistors and stuff, but a lot of times they're MEMS devices in there. And these are used in wide range of things. Your consoles, your game consoles, in this picture, I know it shows the Wii, but your Switch, Xbox, PlayStation, they all have MEMS devices in them. Some of the first earliest MEMS devices were actually airbags. So your airbags in your car, again, those are deployed using MEMS technology. And now your car has, if anyone's, or if any of your parents have bought a new car in the last, even 3 or 4 years, they have sensors everywhere. They can detect if changing lanes, all that stuff. All those are done using MEMS technologies. So it's a wide range of applications, not just the ones that I'm talking about today. So one of the first questions that I get asked a lot by students is, if you're interested in MEMS and you see what what me and Dr. Pyle and stuff are talking about, they say, what should I study? What should I study if I wanted to go into microsystems or MEMS? And the quick answer is anything, any STEM area. These are very multidiscipline areas. So you need electrical engineering, you need mechanical engineering, you need material science, chemistry. As Dr. Pyle was showing, he showed you in the clean room, a lot of the stuff that we do to make these devices requires chemistry. So and a lot of those chemicals can be fatal if you get them on you and everything. So again, you got to know what you're working with. So even quantum physics, all this stuff. Now, I'm not saying you have to be an expert in all this stuff to be a good MEMS engineer or technician, but again, the more knowledge the more area, the broader your knowledge, the better engineer your make. So again, but I've had people in my group. I have people that are in mechanical engineering. I also supervise students in chemical engineering and biomedical engineering. In electrical engineering. So really, and like I said, I've worked with people in civil engineering too. So everywhere, they're all, it all feeds into MEMS. And that's why I like MEMS, because I like to learn stuff. I'm always trying to learn new things in new areas outside of my discipline. So I like being very diverse knowledge. So now I'm going to go into some of the applications that we work on. So the first application, like it says, energy harvesting. So this is sort of a hot topic. A lot of people are interested in this. So the initial question that people often ask is, so why are we interested in microsystems energy harvesting? You know, people know, you know, if you've driven around New Mexico or California or any of those, you know, you see these wind turbines, you know, that are harvesting energy. Now those are harvesting megawatts of energy, you know, power cities and everything else. We're not, the MEMS devices, these little tiny devices, you know, that Dr. File was showing you, those, you know, we're not going to power, you know, like cities and everything. What we're trying to power is something called the Internet of Things. So we're trying to power these sensors. And really the Internet of Things, some of you may have heard of it, some of you might not have, you know, but it's all around us and it's only going to increase. So the Internet of Things, you know, everything. You know, I want to know what the temperature is in the room that I'm in. I want to know what the humidity is, you know, and want this. So eventually you could have it a smart building. So like if I come in, you know, if I come into this room, the air conditioning can kick on, you know, and it could detect, oh, there's one person in here. So it needs to be, you know, I need to turn it down at this such and such power. And then as I leave the room, it would turn off automatically. So it'll, again, help save in energy. You might want it on top of a bridge to see, okay, is this bridge going to fail? Is it going to, you know, is it going to collapse? You know, is it, you know, so structural health monitoring, water, you know, parking lots, you know, everywhere. You basically, you know, in the future, and even we're not talking about like 50 years in the future. We're talking about in the next 5 years or so. You know, they're talking about having 50 trillion to 100 trillion sensors around the world to detect all these things. And so the problem is, though, you have all these sensors. Well, all these sensors require power. You know, if you try to transmit data and everything, what is, you know, like using Bluetooth or any other wireless technology, again, how do you do that? Well, for all that, you need power. You need some electrical power. And right now, they power these things with batteries. But batteries, as we all know, die. You know, and it can be very costly. You know, you're talking about 50 trillion sensors that need batteries. You know, it's good for the battery industry, but not good, you know, because a lot of times these are in remote areas, like I said, the top of the Golden State Bridge, you know, which again, paying someone to go up to the top of the Golden State Bridge to replace a battery, you know, which the battery might cost, again, very minimal amount, you know, dollar less, you know, but yet to pay someone to do that could, you know, again, thousands of dollars. So, you know, so it could cost thousands of dollars just to replace a battery. So what we want to do is create a self-sustaining device, something that can harvest energy from the environment and then the sensor. So there's, you know, a lot of people with photovoltaics, solar cells, you know, you see them on top of even houses and everything else. Those are good for outdoors and they're good for certain conditions. But again, at night or something, you know, they're not so good. So there's different other things like thermoelectric, so that's using heat, but again, those require a large temperature gradient. So what I'm interested in and what we work on is vibrational energy harvesting. Everything is vibrating down at the atomic scale, and everything around us, everything's vibrating. You might not think your house or your building is vibrating, but it is. It's moving at small amounts, but it is moving. So we try to harvest those energies because again, you can. These are vibrations that are happening 24/7. So you don't have to worry about day, night, you know, where they are. The only thing is different applications have different frequencies, so you have to worry about that. But there's different methods. So if you can see my mouse cursor here, so you know, there's piezoelectric sensors, electrostatic, electromagnetic. These are the three big ones. The one that I'm focused on is piezoelectric. So let me see if this works. So here I have a piezoelectric material that if you can see it, and it's connected to this is a light, just an LED light. So let me turn off some lights here. Okay, so I just turned off the light here. So if I shake this, hopefully you can see, I don't know, I can't, my screen isn't big enough to see what I am. Hopefully you can see I'm here, this orange light lighting up. I'm putting it next to my black shirt, so hopefully you can see it a little bit more. But as I shake this piezoelectric film, it's converted mechanical energy to electrical energy. in the form of, and you can see it through the form of creating light. And this is how these type of devices work. Now, the hard thing is we want to make these very small, and I'll talk about how small in a second. But here's, in this picture here, so this is one of the devices we made. So these are 4 sort of cantilevers, or so kind of like a diving board, like a spring-like structure. And this is a AAA battery. So again, we can fit like 4 of these in this, about the same size as a AAA battery, and these can harvest about as much energy as a AAA battery. So therefore, we can replace a complete AAA battery. And we want to be able to put these inside buildings and everything else. And you can stack more and more of these if you want more and more power. So yeah, so we want, one of my main things is I want to be able to put these inside the walls of buildings. So that's why we need these things to be small, because I need to have them embedded like into the walls. And then you don't, because obviously you don't want to go in and break the walls, so you don't want to, replace the batteries. So again, if we have a self-sustaining system where these can, then you can put a wall in there and have it embedded, and you never have to worry about it. It's always going to function. It's always going to work. Then that's obviously ideal. This just shows one of our cantilever structure. So this is our piezoelectric film down here, and this is this is actually quite large. Dr. Ply was showing some of the MEMS devices. They were, on the order of like a human hair. These are actually the whole structure is actually quite large. This is about 5 millimeters in length, which is still quite small actually, but it's still, for MEMS it's quite large. But the layers in here are actually nanometers. So again, smaller than, much smaller than human hair, which is, like 50 to 100 microns. But we need this big proof mass to get to the low frequencies. This just shows one of the devices working. So again, this is about 5 millimeters in length here. But here I'll show it running. So this is, showing, it's basically like a springboard, or like a diving board. And again, the piezoelectric film is just right here. So again, as this bends, as it's due to some vibration, it's creating stress in this film, which then this film, as I demonstrated, converts mechanical energy to electrical energy. So you're able to get electrical energy out of these. Next. So one of the questions that people ask is, so why are these not available? I've shown you that these things work. Why are these not, already? Why are they not, around us already? They have many different problems. These are some of the ones that, again, the power is still not quite where we need them to be. As you scale things down, power goes down, and it's not linear. It goes down, exponential. So the smaller we make these, the less power we're going to get. So we're working with electronic engineers all the time. We're trying to get them to decrease the amount of power that they need, while we're trying to increase the amount of power that we can give them. And hopefully we can, in the near future, we can come up with something that meets all the specifications. Wider bandwidth. So a lot of these devices, they operate at a very specific frequency. But most things like car engines, like the frequency, the vibrations that you get from your car engine, it's going to change from when you first buy it to when, in 5 years or so, down the road, just dust and everything else, this changes your frequency. So trying to develop wider bandwidth frequencies. Application process that Dr. Pyle was like showing to make these things is quite complex. It's more complex than say like transistors for like Intel making semiconductors and stuff. It's, when you're dealing with different layers, different materials, different topographies, it becomes a lot more complex. I just wanted to show this just because it's a cool video. This is actually one way that I'm trying to widen the bandwidth. So here I have a piezoelectric cantilever or film, and then this is a big mass that I have in here. But what I did, instead of having a solid mass, I took a hollow mass and put liquid inside. So then when I put liquid inside, as this bends, you're going to create a sloshing effect of your liquid, which causes a wider bandwidth. So see, it's just a cool video, I think. You see the inside of the liquid. But this is basically changing where the center of mass is, which is changing then the frequency of your cantilever and widening the bandwidth. To lead into my biomedical talk, So what I've done, so again, I come from a background of biomedical engineering. So I'm always working on, I might work on stuff like microelectronics, but then I try to figure out, okay, how can I make this into a biomedical? How can I relate this to biomedical and transition the technology to biomedical? So again, I've been working on energy harvesting for over 10 years. But a few years ago, I was okay. Now, can we transition to biomedical? How do I make it implantable? I wanted to create an implantable energy harvester. And we were working with a company. This is actually about a €7 million. It's about $10 million project working on, where we were working on harvesting energy from the heart to power a pacemaker. So the next generation of pacemakers is actually this, what we call a leadless pacemaker. So this is your typical pacemaker, which a lot of you probably have seen some pictures of or something. So you get, the pacemaker itself is implanted up your shoulder area, but then you have leads, electrical leads that go into the heart. Well, they found the #1 failure mode was of these leads. People sat there and played with them because you can feel them underneath your skin. So they sit there and play with it, or whatever, and they get tangled and they, break. So what they started working on then is leadless pacemakers. So if you look, so you have like a heart here, and so what they do is they put all the pacemaking stuff into this little capsule, which you can see down here on the lower right hand corner. But they take all this stuff into a capsule, and then they can screw it into the heart wall, and then that can do it. And one was just FDA approved last year or so, but those use batteries. The problem with batteries, though, is you can't go and replace this. When it's screwed into the heart wall, you can't go in there and unscrew it. It will cause a rip in your heart, and yeah, obviously that's not good. So they can fit 1 or 2 of these in there in a lifetime. Well, the battery lasts for 5, maybe 10 years, maybe only 2 years, depending how often the person needs their heart to be paced. Well, I don't know about you, but if I have a pacemaker, I want to have the chance of living for more than 5 years or 10 years. So we're looking at, okay, can we replace the battery that's in there with an energy harvester? Now the problem is, see again, I don't know how it's going to show up on my screen, but so I want to take this piezoelectric film, basically, that I got, and make it into fit something very, very small, such as this little capsule here. Not easy to do, and still get the high power that you need. So that's what we were working on, to basically help create a self-sustaining, pacemaker. So leading into some biomedical applications. So what do I got? 10 minutes? Okay. So I'll try to go through this a little bit quick. So during my PhD, actually, this is what I worked on during my PhD. I was working on neuroprosthetics. So sounds fancy. Basically what we did is we took these electrodes, implanted in the brain. Now we were working with animals, so like rodents and monkeys. But the goal was to control robotic limbs, or like a wheelchair or a computer, so with just your mind. So this is especially for someone who's like paraplegic, so they have like, they're paralyzed from the neck down, like their normal day function, is not very high. But if we could give them the ability to control like a mouse cursor, or control their wheel with just their mind, to go simple commands like go forward, left, right, rotate, something simple like that, again, that would be a huge benefit. Now, there's a lot of robotics, figuring out the signals, what someone's trying to think, all that kind of stuff. What I was focused on, though, is just this part, just implanting electrodes into the brain. And people have been working on this since 1970. And yet we still do not have one available. So it's been something that's been going on for 50 years. Now, there was a couple human implants within the last 10 years, and they showed 80% accuracy of controlling a mouse cursor. The person could send an email and stuff like that. But again, it's the longevity. It lasts for maybe a couple years or something, but it doesn't last again for 20 years, because you get all this scar tissue formation once you implant something. So there's still a lot of work going on in that area. What we were working on to get around that is we created movable electrodes. So these center pieces here are the electrodes. These are small. This is, here you see the Sandia, so we collaborate with Sandia. These are small, about half the half of the width of a human hair. And you can see here, I'll turn this on. And what you'll see here is this starts to move down. It's moving down very slow. It's only moving at about 8 microns per step. So, again, the human hair is about 50 to 100 microns. So, again, cut a human hair into about 10 slices, and that's, about how far it's moving down. But see, these are all done using MEMS technology. So if you look in here, the size of these things are about 1 micron or so, so much smaller. And you can see basically what we're doing is we're applying electrical bias, which heats these up. So you see these things start to get shiny. That's because they're getting hot. So these are called electrothermal actuators. So we're using electricity to heat these, and that's causing heat. When you apply electrical bias, that causes them to heat up, and that causes them to bend. When you apply heat to metal, it wants to expand. So that's what's happening here. Let me go on to the next line. So we also worked on some stent projects. A lot of people know someone that's had a stent, so that's why I put here on here. So we worked on developing smart stents, so we could try to detect when when a reclogging of the artery happened. Kind of skip that for now since we're running out of time. We worked on hydrogels. So some of you might be familiar with hydrogels. You might not have heard of it, but you might, seen some. They're often used in a lot of like toys and stuff like that, like where you put, basically it's a gel, you put it in water and it swells up, and it can swell up to 1,000 to 10,000 times. We're looking at trying to make smart ones to prevent clogging of the arteries. So if you had a bleeding on your artery implant, inside your body, you could go and put this hydrogel there, and it would swell up into the blood and stop the bleeding. And here's a picture. Sorry if you're a little bit squirmish, but here's one where we put it inside a sheep artery, and it swelled up, and we showed it worked. And there's the other one on the right, just the device that we used to implant it. So, biosensors. So I do a lot of stuff with biosensors. So looking at all different types of applications. This is one of the devices I worked on. So I was actually, I had a project working with Intel up in Oregon. And so we made these devices for them. They wanted to detect a single particle. So like they were using it in the clean room. They wanted to see if a single particle would land on there, if they could detect it. So basically if something lands on here, I can detect the mass. And this is about 300 microns, so about 3 human hairs. But then there's all these added features which you can't even see on the computer screen that are inside here, that if you zoomed in, you would see, a lot of other small features that are in the nanometer range. So we've worked on using these we're making the first sensor to detect ovarian cancer. So far there isn't one, so we're looking at doing that, working with someone at University of Toronto with that. COVID-19. So actually I was trying to, back before, the COVID actually outbreak happened, back in February, I submitted a proposal to NIH on this topic, saying, okay, we can look at the viral, the antibodies to detect, coronavirus. At that time, they laughed at me. They said, that's stupid. We don't need to do that, Now there's, how many companies are actually working on this antibody, COVID-19 testing. So, but unfortunately we didn't get the funding, so we couldn't do it. But yeah, that's how things go in a lot of research. I'm using it for detecting carbon dioxide, particle sensing, for pollution and stuff like that. I've worked on one company, I can't name who, but wanted, again, to put these sensors in your phone. So again, it wouldn't tell you necessarily the pollution, but they were using your phone. It wasn't in this country, but yeah, in another country, they were looking at put this in a phone, and then they could detect pollution in the air, just, without people knowing it, kind of. So there's a lot of sensors in your phone that, again, they might be there for other applications too, that you might not even know about. Aerosol. So Dr. Pyle, so all of these, yeah, was working with me on aerosol generators. So we're looking at, so if anyone knows anyone that has asthma, a lot of times they use like these drug delivery devices. So yeah, the thing that the ones that are commercially available don't use MEMS or microsystems technology. But the one with microsystems technology, we can make small bits. We can get better drug delivery, more therapeutic, less drugs, so you don't waste as much. So it's a lot of different benefits to this, and potentially it could be made cheaper. Although in the medical area, it's not that huge of an issue. But we're also looking at using this type of technology for additive manufacturing, such as inkjet printing and stuff that was mentioned, and also even microthrusters. So I'm working on a project right now where we're making this into space, like we're using this for space applications. Again, if we can put combustible material in here, again, we can create microthrusters using this. And here I'll show a video of this, the aerosol. Again, here's our device and showing aerosol coming out. So again, you can think, if you had it connected to something, it would be shooting off in the opposite direction. Okay, next slide. Let's see. Okay, I'm almost out of time, but microneedles. So we work with. So I work with the medical group at UNM on making painless microneedles. So these are, again, if you've seen the commercial for the diabetic patch that people put on, so these again use this type of technology. So these microneedles, you just touch it, it goes into your skin, but they're painless because it doesn't go far enough, doesn't go deep enough to hit a nerve. But you can coat these in drugs to deliver drugs. You can put different stuff on there for allergy testing. And again, you can see that using MEMS technology, we can make a lot more. We can put a lot more needles in an area that was same size as one needle. So again, we can do more type of testing with this. I just want, this is like one of my last slides. I think I've just a question slide on the next one. But just showing you, we don't just work on these areas, biomedical and energy harvesting. If you're interested, we do robotics. We make e-skin kind of stuff over here. So like, technologies, robotics, so you can, soft tactile sensors for robots, ultrasound transducers, you name it, microphones, speakers, all stuff for your phone. So work on a lot of different things, not just what I've talked about here. But anyways, yeah, open it up for questions, yeah. Or comments or anything. Let's see, let me see if I can.
There's nothing in the chat.
No.
These guys are so chatty.
And if you're interested in MEMS, like I said, the one thing that I liked with it, like I said, when I was your guys' age, I didn't know anything on MEMS. I didn't even know what an engineer was. I know when I went to my guidance counselor, about like what to do in college and stuff, they're like, oh, you should go into engineering because I was good at math, and I was like, I was like, okay, I thought engineer, I was thinking it was, someone, a train conductor or something like that. I was like, I don't know what an engineer is, so yeah, so it was I didn't know nearly as much information as you guys, have at your age. Again, I know Dr. Pyle is the class that they offer that high school students can take, so it might get you interested in MEMS or engineering in general. Like I said, MEMS, like you can always switch. Like I said, it's really, if you're interested in chemistry, you can always go there. And then as you go on to get your, where you want to work in, or if you go in to get your graduate degrees, then you can go into MEMS. Now that being said, we do have, so at in the ME, the mechanical engineering department, we just got approval we have a new concentration for undergraduates in the MEMS area. So if you go into the mechanical engineering department, you can get if you get your undergrad in it, you can get a concentration in MEMS by taking 3 courses that me and Dr. Pyle teach. Or if you think you might be interested in this, yeah, it's something to look at. And if you do go into, oh, sorry, go ahead.
Sorry, no, that's okay, Nathan, go on.
Oh no, I was just going to say, if you guys, if you go on to UNM, and you want to do undergraduate research, I know Dr. Pyle was saying he just got an undergrad, and I'm always interested in having undergraduates come and do research in my lab. Dr. Pyle is too, I know. So yeah, so, hit us up. I know the last time there was a question on, can high schoolers come into the lab? Yes and no. It's tricky, but yes. So last year I did have a high school student from La Cueva who came and worked in the lab. Of course, then the Corona thing hit, so she didn't get as much done as she wanted to. But yeah, and right now within the next year, yeah, I would say yeah, probably not. But but once the Corona's lifted and stuff, seniors it's easier to get, or if you're over 17 years old, it's easier to have you come in and do some work in the lab. Under 17, it's difficult. So, but not unheard of.
Elsa, what are the, or Nathan, what are the other concentrations in ME?
We don't have any other one. That was our first one.
Oh, really?
A lot of the other departments do have concentrations. Like electrical engineering, they have concentrations. You can go in power, and some of the other ones I don't remember. Chemical, I think require you to have a concentration. Chemical engineering, but no, ME actually we don't have any concentrations. So me and Dr. Pyle, we submitted something, and we're the first concentration, and I'm hoping in the future, of course, maybe when you guys are there, that I want to actually have the concentration also in electrical engineering and maybe chemical, because like I said, MEMS is everywhere. So I mean, like I said, it's in electrical engineering as well. So I want to try to broaden the concentration to other departments as well. But that's in the comment. Or no.
Elsa's going to say something.
Nathan actually wanted to bring it up because although it's not an official concentration, we do have the aerospace component that the mechanical engineering is working. The students can do their classes. We don't call it concentration, but maybe it's more of a focus.
Yeah, the aerospace. So we have that's for graduate students. So we have one for graduate students and stuff. And then we do offer the mechanical engineering department for your capstone project, for your senior project. We do have the race car and stuff, which is that's a separate thing. It's not really a concentration, but it's something similar. But they have that. They have the solar splash. So again, if you're interested, so we have a lot of different things to do for your senior projects and stuff.
Yeah.
But if you did, where we don't have an aerospace and aeronautics specific degree, you take all the classes that you would take for that, and
exactly. And I mean that's what you do. Undergraduate classes, you're mostly, whether you take them again at, wherever the ones you take at MIT versus say UNM. Again, they're going to be the same classes, or if you take them in India or you take them in China, again, a lot of the courses that you're going to take are going to be similar, except for maybe some of the special topic ones and stuff that you choose. But yeah.
And one thing that you were saying about math, I don't know if you guys know, but for some departments, you can get a bachelor's of science or a bachelor's of art. And the difference is how much math you take. In engineering, it's not quite like that. But so for some of you, like in biology, you could get a BS or a BA, depending on how much math.
Yeah. And like I said, if the engineering, unfortunately, math is a part of engineering. So you do have to be at least sufficient in math. But like I said, if you're still interested in this area, like Dr. Pyle was saying, like technicians and stuff, I mean, can make, it depends what type. I mean, but there's always, most of the people that actually go in and do the actual work, get intel and stuff, are actually mostly technicians. The engineers are supervisors, they're telling, but yeah, I mean, my brother's technician and stuff, and I mean, he's, doing fine and everything else. And a lot of times he knows more, even though he might know more on a certain machine than I do, just because, again, like I say that, again, just because you have your PhD or something doesn't make you, any smarter than some of the technicians and stuff, in the MEMS area, experience means more. You get the hands-on experience. That's what it's all about.
Yep. Okay, guys, not one question for Dr. Jackson. I think what he does is so cool.
Yeah, usually if it was in person, I would have like a library of devices and stuff to show you all these stuff, because it's much cooler to see it up front than it is to see it on a computer screen. On the computer screen, I know I say the size scales, but it's hard to, even for me, it's hard for, to judge how small it is until you actually see some, and you're just like, okay, you can't even see it with your eye, and then until you zoom in and all of a sudden you see, all the problems or all the cool features. It's really, like I said, taking, this area. I mean, I just think it's fascinating to take like a machine that, how it works, like gears and stuff, like on a large scale, then shrink it down to smaller than than like the red blood cell or something, and it still functions and works. The physics behind that and stuff is quite neat and fascinating.
Itty bitty living space.
Yep, exactly.
Well, thank you so much again for doing this. I really appreciate it. I enjoyed this
Thank you.
every time I hear it.
If anyone does have a question, there's my email's up there. So yeah, just email me. And yeah, I'm always.
And thanks for being so friendly.
Thank you, Nathan. Thank you so
thank
much.
you.
Thank you again.
Thank you.
And then let me tell you about Dr. Nathan. Did he leave yet?
No, I'm still here.
Yeah, I'm very happy to let you know, part of this program is funded by the program that you mentor a student from Puerto Rico last year.
Yes.
And the good news is that we have been recommended for next 5 years of funding. And
very good.
I might be giving you a Puerto Rican student soon. So if any of these students come to UNM, these high school kids, and they want to work with you, there's a possibility. And this one, we are going to have undergraduate research. I might be able to give you a student throughout the academic year as well.
Very good. Yes. Yeah, the one I had last time worked out good. We even published a paper together. So yeah, worked out great.
It's amazing. Yeah.
Yep.
Thank you. Appreciate it, Nathan.
Yep, thank you. Yep, bye.
Okay. So tomorrow we have the land art, and I sent an email to you guys. I hope some of you got it, about getting ready for presenting tomorrow. All right, Matthias is nodding yes, so he speaks for all of you. Okay, guys, so I will see you all tomorrow. And thanks for all of your attention, because we had 3 speakers. That's hard to sit through, I know. Have a good evening.
Bye, Steffi. Thank you.
Bye, Elsa.
Take care.